So what I would say here is that momentum is a system parameter. Instead of a single object. So what do I mean by that? So as an example here, let's think about kicking a ball with your foot. And I know that seems kind of obvious to say kicking a ball with your foot, but what do I really envision when I see this? Most people, they see a single object. And in this case, it's going to be the ball. So I imagine that I have a soccer ball, right? And so you could imagine that if I have some soccer ball, I don't know how you draw those symbols on a soccer ball, but they sort of like have these kinds of shapes here. And then somehow these guys are all attached to a central object. So let's say that this is my soccer ball. And then what I'm going to see here is that I have my foot that's going to come down. And I imagine that my foot's going to come in. And because this is soccer, they might have spikes to grip the that. And then we need our Adidas stripes here, right? So we imagine that we have a foot that's coming in. So when I envision a single object, then I come in here and I go like, what I'm really focused on is on the ball. So then what I see here happening is that I see that I have a force coming in, which is the force of the foot. And this force is external to the ball. Oh, wait. Let me be careful. That's just the force of the foot. But because the foot is external to the ball system, then this experiences an external force that's not equal to zero. When you do that, then you use the impulse momentum theorem. And what the impulse momentum theorem says, that this external impulse is not equal to zero. So that means that the impulse changes the momentum of the ball. So that's a pretty standard view when people say like, oh, that actually, you clearly kicked the ball. Well, what's more important, believe it or not, is not a single object. Momentum is a systems parameter. So now what we have here is that we have a system of objects. And what do I mean by a systems of objects? What I see here is that I'm envisioning the foot plus the ball. That's my system. So now if I look at the same type of situation here, where the foot is coming down and it hits here, right? And I got my spikes again. I got my Adidas stripes. And then I have my ball right here. And in this case, let's not try to draw that fancy ball anymore. But what I'm seeing here is that this is my system. And so when I look at the system, I then have Newton's third law. So what does Newton's third law says? What it says here, that my foot applies a force to the ball, and there's an equal and opposite force of the ball applying a force on my foot. And so what we then say here is that if this is the whole thing, then we say that the net force in this case, which is the external force, that here in my system, I then get that the force of the foot plus the force of the ball, by Newton's third law, they're equal and opposite, and that is 0. So when this is 0, then this tells me here that then the net force is equal to the change in momentum of the system, and this is 0, which then means that the momentum of the system initially is the same of the momentum of the system in its final state. So if I have an isolated ball, I have to use the impulse momentum theorem. If I have a systems of objects, then there's this thing called conservation of momentum. And I haven't written anything about that, but I would say that conservation of momentum is the second commandment of physics. Conservation of energy being first, conservation of linear momentum being 2, and conservation of angular momentum being the third commandment of physics. They are the most powerful without any doubt. And all of physics relies on those things to a large extent. Now, that being said, I want to go back and talk about where I started off here, which I sort of like lost track of where I was going. So what I want to do here is that Newton's laws applied to a system of interacting objects leads to conservation of momentum. Be careful, conservation of linear momentum. And that's a big deal in physics. That is a huge, huge deal in physics. So what do we know here? The best way to understand how a system behaves is following the center of mass point. And this is what we've been doing the whole time. If we looked at motion, we looked at the center of mass point. If we look at Newton's second law and all those things, it was about the center of mass point. But now we have a system. And here's what we know, that if a system experiences an external force that's not equal to 0, then what it tells me here is that then the system has parameters. It has a center of mass position, it has a velocity center of mass, and it has an acceleration center of mass. And as a consequence, it follows all of the things that we did before. If a system experiences no external force, then the system is in equilibrium. And when we say equilibrium, we mean it's either at rest or static equilibrium, or it's moving at constant velocity, which is what we call dynamic equilibrium. So when I look at static equilibrium, what that really tells me here is this. So for a system in static equilibrium, the center of mass, which I'm now going to write as Cm, the center of mass does not change. Before and after some interaction. If I have a system in dynamic equilibrium, then the center of mass velocity does not change before or after some interaction. So that turns out that what ends up happening is that that becomes the most important thing. Linear momentum conservation is about keeping the center of mass velocity, and this is what I'm going to start writing this as, the center of mass velocity equal to a constant. Linear momentum conservation is about keeping the center of mass velocity equal to a constant. This implies that the system must adjust itself to keep the center of mass equal to a constant. So the system must adjust itself to keep the center of mass constant by adjusting the individual momentums of the system's objects. That is essentially what momentum means right there. It's quite complicated, if I could say that. It's very, very, very deep. And I don't want to get too deep into that, But the picture that I tried to do last time, it looks something like this. And then I want to try to move away from this. So what I did beforehand is that I chose an example here. And it goes something like this. Imagine that I have a block. And this block will be this guy. I'm not exactly sure what I did last time, but it's got to be close to this. And what I'm going to see here is that this guy is moving with some momentum P1 in that direction. And then I'm going to have a second block. Let's say that this block is like this. So if I look at this block, I'm going to call this guy here. And in this situation, I'm going to say that this momentum of this block initially is 0. So what I'm going to do here is that because momentum is a system thing, I'm going to come in here and just say, this is my system. Now, these guys are going to interact with each other. And I'm going to say that this is what happened beforehand. So when I see here is that I'm going to ask the question, are there any forces within this system? When these guys collide, we're going to see that I'm going to have the force of 1 acting on 2, but then I'm going to have an equal and opposite force of 2 acting on 1, so that the net external force is going to be 0. All of those forces are going to cancel within the system. As a consequence, that tells me here is that momentum of the system does not change. So what does the momentum of the system not changing? Well, if I look at the center of mass of this thing, I could imagine the following picture. The first thing that I would look at is that if this is the center between the 2 blocks, note that block 2 is bigger than block 1. So I would expect that the center of mass will be closer to 2 than to 1, just because it's a little bit bigger. So it doesn't really matter. So this is the center of mass. So the center of mass is now moving. So I'm going to say that this is the direction of V, center of mass. So conservation of momentum is about keeping V, center of mass, fixed. So then blocks 1 and 2 have to rearrange their momentums to be fixed. So what do I mean by that? So I'm going to go to a bar diagram. So when I go to a bar diagram, what I see here is that I see something like this. I see that the momentum of block 1 is going to look like this. So what am I going to do? I'm going to pick this to be my positive direction, this to be my negative. So P1 is moving in the positive direction. So here is where I have P1 initial. When I look at P2, P2 has no momentum. So therefore, P2 initial is 0. So when I look at my total momentum of the system, this tells me here that this guy has to be a constant. Okay, it has to be a constant. So now that means that P1 and P2 have to adjust themselves to keep that constant. So what's most likely going to happen? I don't know what the initial momentum of 1 is, but a reasonable scenario here is that P1 is then going to move in the opposite direction. let's say that it bounces in that direction like that. So one bounces back, so then it forces two to go in the opposite direction. By the way, I put an initial there. I should have put, let's say, to final, and then I'll write, ooh, I wrote that wrong again. To final, and I should have written this as P1. So these guys have to adjust themselves to keep total momentum constant or the center of mass fixed. So now what happens here? What happens here is that if you look at the green is now P1, or block 1 is moving in the negative direction. So what happens here is that now P1 is negative. And because it's negative, then that means that P1 final is going to be like this. So then P2 has to adjust himself to make sure that that's constant. So if this is negative, I now have to choose the momentum of 2. So the momentum of 2 is going to change its value in such a way that it does that. In other words, these momentums after the collision must readjust themselves to conserve momentum, which is equal to saying keep velocity center of mass constant. And again, this is after, which I did not write. Now, that's a really, really abstract way of thinking of things. And that's all I'm going to say. I'm not going to say any more than that. I should have done this last time. But what I want to do here is that I want to review very, very briefly, because there's a lot here. So momentum is a distance parameter. We could think of this between a foot and a ball. So the foot kicks the ball, and either I could focus on the ball or I could focus on the system. If I focus on the ball, then I have to use the impulse momentum theorem, which is effectively using Newton's second law to get a sense of what is going. So then the impulse by the foot changes the momentum of the ball. On the other hand, we have a systems approach, and this is the power of momentum. This is how physicists use momentum. We look at the system, and by looking at the system, Newton's third law tells us that there's equal and opposite forces, and so therefore the net force on the system is 0. So now the change in momentum is 0 as well, and that tells me that the momentum before and afterwards are the same. So now when I look at interacting systems, if I have a net force that is 0, I could either have a system that is accelerating or a system that's in equilibrium. When we focus on momentum, we think of a system in equilibrium. But there's two cases. There's static equilibrium, which tells us that the center of mass does not change before and after an interaction. But momentum is about dynamic equilibrium, where the center of mass velocity does not change. So then I tried to set up a picture here to show you that the system must adjust itself to keep the center of mass fixed. So if I look at the center, the velocity center of mass is fixed, momentum implies that they adjust themselves to keep the momentum, the momentums of the system will adjust themselves to keep the total momentum constant or the velocity center of mass fixed. And that's what I mean about this center of mass. If it continues to move after the collision, that center of mass still has the same velocity moving to the right. It always moves to the right. And that's the way we're going to capture this on a bar diagram.